Kind of fun. It's kind of funny. Um, I spent 40 minutes in the video before, and it's so easy. I mean, I just walk. I was like, it's all. But it's funny because it took me like, like just reading these, read these, like, and kind of I now understand. Like, I think and I want to I'm recording because I want to make a test, see if if the example here from Michal matches. But basically, it's really, it's I think it's kind of fairly straightforward, and I kind of, I don't know, I was just like sleeping on it, and then it's like, it, of course, it's obvious that it's this, but I might be wrong. So basically, the idea here is that it's all about the encoding. So I was kind of a bit wrong when I was saying that this is a generic circuit. It's not a generic circuit. That is a particular one for a concrete graph. So the idea here is I'll pin here. So the idea here is you encode. So the encoding idea is the one that I kind of took from here. Is that you basically so you're basically you encode by putting zeros and ones, whether they're in one group or the other, and then the edges are encoded in the circuit. So if you're connecting these two qubits, this means there's an edge between this qubit and this qubit, or this vertex and this vertex, and the same here and the same here and the same here. So this is what this first part means. And at the end of the day, what you're doing with these, right, is you want to flag. So you want to kind of flag by flipping the phase in those cases where there is a 1 and a 0. So because that's, let me see if I can clear the circuit, because you want to basically flag those items to then be able to kind of the whole concept here is you basically want to add a phase and in those edges where the qubits are different, because then when you will do the rotations on the x-axis, which will kind of play with the different amplitudes, they will interfere. Exactly. And when they interfere, then you will bubble up the solutions that you've been flagging. Because the whole idea here is I believe I kind of don't understand why there's the Hadamard's in here, because I would rather say the Hadamard's go in the very beginning, unless the circuit is being read the other way, which kind of doesn't make much sense, I think. Because for me, this makes sense that you're doing that on a superposition, so you have all the possible splits, right? And then you're kind of going to surface the ones that, yeah, the ones that matter. So I think that's the trick. And I wanted to kind of do a quick thing here. So, and the reason this works, the reason this works is because, so if it's a 0, 0, right? See, that's why I don't like that rotation. This shouldn't be rotated right now. So that's the wrong. I will just use maybe. I just want to use exactly. So just going to use a 16th or like a quarter turns. Yeah. So I don't know. I have to still work on how to make that the way I want it, because the idea is now they're both from the same group, so there's no phase added. If they're both one, there's also no phase added, because basically what is happening is it turns that into a 0, so the phase is not happening. And because the phase is not happening, then here there's no even phase kickback or anything. But if you have like a 0 or a 1, then you've got a phase, right? And the same happens here. If you've got a 0 and a 1, then you also have a phase, because then it means those two qubits are, those two vertices are in different groups, and that's what you wanna. That's kind of the unit, and you wanna do that per each edge, right? So, and that's what I want to do with this example here, because I know the two solutions. I want to validate that those solutions are correct, and I'm gonna try to use. The thing is, I don't know with the angles. I don't know if those angles are gonna surface those solutions as well. We'll give it a try, but I would assume that this is qubit 0, qubit 1, qubit 2, and qubit 3. So we've got an angle between. We've got 0, 1, we've got 0, 2, we've got 0, 3, and that's it really. There's nothing between 1, 3, 1, 2. Exactly. So that's going to be 0. Like, okay. So that's qubit 0, 1, and then I would simply, kind of do the same with the other qubits. So, and that's all that it takes in theory, if I'm correct, if I'm right. So it's all from the qubit 0. So that's all there is. There's no other. Yeah. So, but you still need then, because that just gives you the phase. Like, now the idea is if I put all those into superposition, so what you get is you're kind of doing that over all the different possibilities. So if I put the chance display in here, resize it. You see this all, like, you don't see, despite the fact that you have actually some other phases, but there's no, the amplitudes are all the same. So that's why you add X rotations, which I'm going to play with this as well. Let's see. And as you do that, you can see that the probabilities are basically changing because some of those solutions are flagged. Yeah, and so you have these and these, but I think these are not the solutions that I'm looking for. It's 1, 0, 0. So those ones I'm looking for, and that might just be because the. So what is the difference of doing the Hadamard's here and doing them here? Does this make any difference? Yeah, of course. I mean, the idea is you need to be flagging on a superposition, right? You need to be flipping the phases on a superposition, because what's the point otherwise? The 1, 0, 0. So in theory, this is the one that we're looking for. For some reason, those are the ones that are being. So 0. Yeah, that's correct, right? 0, 1, 0, 2, and 0, 3. So those are the 3 cards you have. Yeah, I have this here. So, okay, yeah. So these and these, but because it just might be I'm using the wrong angles. That's the thing. I wanted to kind of parameterize that. So this is basically. What if I use a spinning? That would be nice. What if I use a spinning here? What is the? That's cool. You see? Oh, that's nice. So I should be able to, at some point, the solutions they're looking for are these. That's interesting. What if I use also like a spinning X? That's interesting. If I could basically manage that. Because the solutions here are 1, 0, 0, 0, and 0, and okay, 0 and all ones. So we're kind of looking for this one. and this one, yeah. But there's no kind of setup where they are the most. Oh, unless this is flipped, okay, because yeah, I think that's the, I think it's the encoding. I think it's the fact that can I just take the whole can I just take the whole yeah. No, I don't know, it's not gonna work. No, I messed up. Undo. I want to basically, because I think the difference here is again the way that these solutions are encoded, right? I think it's just you gotta flip. It's not big, and it's like this should be the lowest value, and this is the lowest value, not the highest value. And if so, then this is exactly this solution, which at that point becomes and this solution. So there's a point in time where those things become the highest probability, and this is exactly what we're looking for. I don't know. I can't really pause this. It would be cool if I could pause this, but this is the solution we're looking for. 0, 1, correct? Which is this one, right? It's just flipped in terms of the order, and then this one, which is basically this. Yeah, it's also flipped. And if you can see, those are. It's funny because there's also this solution like all or nothing, which is kind of, I think it doesn't make sense at all because you're not maximizing. Those are definitely not valid solutions, but they pop up in some given some configuration. So this is that's pretty nice. I'm gonna save that, and I'm gonna call it QAOA. That's nice. V2 done. Especially that you can see with all the different parameters that you could have, you can see the evolution, and I see that those solutions are the ones being flagged. So that's definitely what it takes, and that's pretty nice. So I just said again, this is just flipped. So okay, so I validated that it works, and that's basically the idea. So as you can see, here is a particular example. But it doesn't have to be like that. So you make those connections based on the way you encode the graph. That's kind of, and here they're explaining is that the generic solution might require you to have an ancilla qubit, but in this case, in the maxcat problem, you don't have to because you can just do it this way, because of the zeros and ones and because the way you translate the problem, so to say. I think intuitively, yeah, definitely, and that's it really. So this is QAOA for maxcat. I really like this. I just would keep, and the idea is, I think, basically, you can take all that. Let's see, and I think you can actually have multiple layers of that. So if I now say, please make make gate and do all of it like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So from 1 to 11, yeah. And this is I'll call it like the alpha or the layer, right? Layer. And I think that the idea here is that you can basically put another layer in here. Ooh, interesting. And another, because you can have more layers, and that basically speeds up these. And the trick is to find how many layers also you play with, and you can see that. But you see that you're not getting them. If you add more layers, you're not getting the right solutions. You're getting like basically. Yeah, you're getting, because this is, remember, this is the solution we're looking for, and this is the solution we're looking for. So they do still appear, but this sort of a hiccup at some point. That's interesting. That's really interesting. Cool. I'll just bookmark that as well. And I should really have a QAOA layer. I think I should just keep those things as a library. I mean, I don't know if they're correct, but I think that's at least I think it's helpful to see it this way. I love this. I really love this. Okay, cool. Now, the next thing that I'll do is a video on how does this translate to this to the actual yellow submarine, because this is all like it's all like discrete quantum computing. And then I realized that there's an actual here there's the actual research paper that Mihao and the other collaborators, like the other people that actually work on the project, published. And here they explain, okay, so the equivalent approach, but for CBQC, so for continuous variable quantum computing. And it's kind of I'll go through that. I haven't really read this, but I just scanned this quickly, and I kind of see that they basically go and say, okay, so that's how you would build the circuit with CBQC, which is this one, right? So those are, and that's where I have like squeezing gates and stuff like that. So, but I need to understand a bit more, and that hopefully will help me understand a bit more. What is the Kerr gate, and you have the cubic phase gate. Exactly. Yeah. So, and that's going to be probably the closing of this project series, because of the yellow submarine series, because it's been pretty long, but I definitely learned a lot of stuff, and actually this tool is just amazing. It's nice. You can see that's a solution, and that's a solution that we want. Yes. Nice. Perfect.